Hello everyone, welcome back to my channel. In this video, I will discuss about damped vibration and damped oscillation and different types of damp. This lecture is mainly for MAKAUT BTech Physics syllabus, paper code PH 101 or 201. Before that, if you are new to this channel, then don't forget to subscribe the channel for more updates. You can also join the Facebook and Instagram page given in the screen for more updates. If you want to join my online classes, then you can contact me through the WhatsApp number given in the screen, and also you can send me direct message through Instagram and Facebook. Let's start the class. So here we will discuss about the damped vibration or motion in a resisted medium. For that, let us take a particle having mass m and it is moving in a straight line under a force which is proportional to the distance towards the initial position of rest, and also the particle is under a resisting force. The mass of the particle is m and the velocity or instantaneous velocity of the particle be v. So for the simplest case, the resisting force may be taken to be proportional to the instantaneous velocity of the particle. When condition is applied, velocity is very small. So in that condition, the equation of motion of that particle would be given by this equation 1, that is force F equals to minus of kx minus of b into v, where F is the force, x is the displacement and v is the instantaneous velocity, k is the spring factor or stiffness factor, and the coefficient v is called the frictional force per unit velocity. So the differential equation 1 takes the form m d2x dt2, that is acceleration, mass into acceleration, that is force, equals to minus of kx minus of b into dx by dt. Or if we divide it both sides by m, then we get d2x dt2 plus b by m into dx dt plus k by m into x equals to 0. So this is the transformed version of the differential equation. Now we take b by m as 2a and k by m, which is the characteristic angular frequency that we have discussed in the previous videos, that is we take omega 0 square. So k by m, that is stiffness factor or stiffness spring factor divided by mass, that term is denoted as omega 0 square, and b by m, that means b is the frictional force per unit velocity, so b by mass, that is we term it as 2a, which is also called the damping coefficient or coefficient of friction. So the second order differential equation for damped vibration takes the form, that is d2x dt2 plus 2a into dx dt plus omega 0 square x equals to 0. So this is a second order differential equation. We mark it as equation 1. Now let us take the solution of this differential equation v, x equals to some constant c into e to the power of alpha t. X is equals to c e to the power alpha t, so x dot or dx dt would be c alpha e to the power alpha t, and d2x dt2 would be c alpha square e to the power alpha t. So if we put this value in equation 1, we get c alpha square e to the power alpha t plus 2a into c alpha e to the power alpha t plus omega 0 square into c e to the power alpha t equals to 0, or we take the common c e to the power alpha t common, in bracket it would alpha square plus 2a alpha plus omega 0 square, that would be equals to 0. So if we take the common c e to the power alpha t, so it will be c e to the power alpha t into, in first bracket it would be alpha square plus 2a alpha plus omega 0 square equals to 0. So the solution for alpha would be alpha equals to minus 2a plus minus of 4a square minus 4 omega 0 square whole divided by 2, or it would be minus a plus minus of a square minus omega 0 square. So alpha has two roots, that is minus a plus root under square minus omega 0 square, and second root is minus a minus of root under alpha square minus omega 0 square. General solution for x would be x equals to e to the power minus at into in bracket a e to the power square minus omega 0 square t plus b into e to the power minus of square minus omega 0 square into t. So this will be the general solution for x. Now three cases may occur for this damped vibration. So let us discuss about that. Now case 1, that is called underdamped condition, where that square minus omega 0 square is less than 0. That means the root under term is less than 0. Or we can take square minus omega 0 square equals to I omega prime, where I equals to root under minus 1. So for underdamped condition, square minus omega 0 square less than 0, or b by 2m whole square minus k by m less than 0, or the condition is b less than root under 4 k into m. So this is the underdamped condition. For that case, the solution of the displacement would be x equals to e to the power minus at into a e to the power I omega prime t plus b to the power minus I omega prime into t. Now if we expand it according to Euler formula, this exponential I omega t and exponential minus I omega prime t, then we get e to the power minus at in bracket a into cos omega prime t plus I sin omega prime t plus b into cos omega prime t minus of I sin omega prime into t, or displacement x would be e to the power minus at. We take common cosine term and sine term separately. So we get finally x equals to e to the power minus at into a plus b into cosine of omega prime t plus a minus b into I sin omega prime t. Now we take a plus b as d sin phi. And similarly, a minus b into I, we take it as d cos phi. So that displacement term would be e to the power minus at into bracketed, it would be cosine of omega prime t into d sin phi plus d into sine of omega prime t into cos phi. So it would be e to the power minus at into d common. This would be cos a sin a cos b plus cos a sin b formula. So it would be sine of omega prime t plus phi. So x would be equals to e to the power minus at into d sin omega prime t plus phi. So this is a solution of x for underdamped case. Similarly, here we can take also the a plus b as d cos phi, and similarly a minus b into I as d sin phi. So for that case, the solution for x would be this one, when if we take a plus b equals to d cos phi and a minus b equals to d sin phi. So according to our convenience, we can take both, and both the displacement, both the equation of displacement takes the form x equals to either sine form or cosine form. That means motion of this displacement is oscillatory in nature. So for underdamped case, the motion of the oscillator would be oscillatory in nature. That means either it will be sine form or cosine form, and the motion would be oscillatory in nature. So in case of underdamped case, the particle will move in an oscillatory motion. So in case of underdamped vibration, the particle will move back and forth about its original position of rest or the equilibrium position. Now the second case is overdamped condition. Here in case of overdamped condition, that root under term, that is square minus omega 0 square, it would be greater than 0. So for that case, omega 0 square would be less than a square, or by 2m whole square would be greater than k by m whole square, or b would be greater than of 4km. So this is the condition for overdamped vibration. So for overdamped condition, the equation of motion would be as per the equation 1 as shown earlier. That means it will consist two exponential term, both will fall to 0. So for overdamping case, the roots would be equal, the value of alpha would be real. So the equation for displacement would be as per equation 2 as discussed earlier. That means x equals to e to the power of minus at in bracket a e to the power square minus omega 0 square t plus b e to the power of minus a square minus omega 0 square into t. So this would be the equation of displacement for overdamping case as per this equation 2. So it consists of two terms which are both exponential. So the displacement consists of these two exponential terms which will fall to 0 as per this equation. So for overdamping case, the particle displacement is non-oscillatory in nature, and it consists of two exponential terms. So in case of overdamped vibration, the motion or the displacement is non-oscillatory in nature, and displacement will decay exponentially with time, and rate is very slow. Now the third case, which is called critically damped case, where omega 0 square equals to a square, or k by m whole square, that would be this b by 2m whole square, or b would be root over equals to root over 4km. So in that case, the roots of alpha are equal. So in that case, the equation of motion would be this one. Third equation would be the equation of motion for a critically damped vibration. These are also non-oscillatory in nature, but here the decay of displacement is very fast compared to other two types of vibrations. Here the motion is non-oscillatory, characteristics motion is non-oscillatory, and decay is fastest. Why this is fastest? Because this contains only e to the power minus of at term. So exponential term which contains a negative power. This equation 3 has a maximum decay rate of displacement compared to other underdamped or overdamped vibration cases. So for that reason, the decay component is fastest here. So these are the three types of different vibration: underdamped, critically damped, and overdamped vibration or damped vibration. Now we will plot the displacement versus time graph for all these three types of damped vibration as well as a simple harmonic motion. So this is the graph for simple harmonic motion curve, that is displacement x versus time curve. This is the displacement versus time curve for damped vibration, critically damped vibration, and underdamped vibration. So if we plot the three graphs in a same graph paper, then it would be like this figure. Here this one is underdamped case, because in case of underdamping vibration, the motion is oscillatory in nature. So this is the oscillatory motion graph. Secondly, for overdamped case, the displacement decays exponentially with time, but in a slow rate. That means decay rate is slower. So this one is for overdamping. Third graph is for critically damped condition, because in case of critically damped condition, the displacement for critically damped vibration will decay exponentially with time with the fastest rate. So here we can see the rate of decay or the or the graph stiffness is maximum. So here this one is the graph for critically damped vibration. Next we will discuss about what are the significance of these underdamped, overdamped and critically damped condition or vibrations. So in case of underdamping case, the motion is oscillatory in nature and its amplitude will decay exponentially with time and it will reach to zero after a certain time. So these are the significances of underdamped vibration. So for case of underdamping vibration, oscillatory motion is present and the amplitude of oscillation of a damped harmonic oscillator decreases with time and eventually it approaches to zero. So this is the significance of underdamped case. Next, the significance of overdamping case. In case of overdamped vibration, the motion is not oscillatory. That means motion is non-oscillatory in nature and the displacement will decay exponentially with time but in a very slow rate. So overdamped condition is a condition where damping of an oscillator causes it to return to its equilibrium position without oscillation. That means it is non-oscillatory in nature. So the displacement decay rate is very slow. Now for critically damped vibration, the motion is non-oscillatory in nature, but the decay of displacement is the fastest among these three. So the system or the oscillator will try to bring it back to its initial position of equilibrium as fast as possible. So for critically damped vibration, condition in which the damping of an oscillator causes it to return as quickly as possible to its equilibrium position without oscillating back and forth about its position. That means its equilibrium position এর about এ কোনো oscillate করতে থাকবে না এবং it will try to bring back the oscillator to its original position of rest as fast as possible. So the decay is fastest. So these are the three significances of underdamped, overdamped and critically damped vibrations. Now we will check different types of questions that came regarding this topic in the previous year or previous semester examinations. So in 2017, a 5 marks question came as a particle is subjected to a harmonic or restoring force and a damping. Its equation of motion is given. Under the condition of critical damping, find the expression for displacement as a function of time. So which we have already discussed. Can you justify why the condition of critical damping corresponding to the fastest non-oscillatory decay? This also I have discussed here. Why it is fastest? Here I have discussed the second part of the question. So in 2013 and 2023, a 4 marks question came in similar topic. That is, write down the differential equation of damped oscillation, solve it for underdamped motion. So for underdamped motion, you have to solve and write down the equation of motion. And 2022 also, a question came as a 5 marks question, that what do you mean by harmonic motion? Give a graphical comparison among the following 4 types of harmonic motion: simple harmonic motion, underdamped, overdamped and critically damped. So you can see all these questions I have already discussed in my lecture. Now we will discuss some practical example of underdamped or overdamped and critically damped vibration. That means some practical, we will discuss about some practical example of different types of damped vibration. The first example is a bouncing car. That means the question is, how would a car bounce after a bump under overdamping case, underdamping case and critically damped condition? That means একটা গাড়ি তখন রাস্তার উপর দিয়ে যাচ্ছে, তখন একটা বাম্পের উপর যখন বাউন্স করবে তখন এটা ওভারড্যাম্পিং ইন কেস অফ ওভারড্যাম্পিং, ইন কেস অফ আন্ডারড্যাম্পিং এন্ড ক্রিটিক্যালি ড্যাম্পড কন্ডিশনে হোয়াট উড বি ইটস স্টেট অফ বাউন্স, যে বাউন্স করবে তার ক্যারেক্টারিস্টিক্সটা কিরকম হবে। ইন কেস অফ ওভারড্যাম্পড ভাইব্রেশন, the motion is non-oscillatory and displacement decay rate is very slow. So the particle or the object or the car will return to its original position of equilibrium or position of rest in a non-oscillatory manner, and also it will take longer time. That means decay time of its and it will also take longer time to reach its equilibrium position. So the car will bounce to a visible extent and takes longer time to reach its equilibrium position for overdamped vibration. If the condition is underdamping, then what will happen for the car? So in case of underdamped vibration, the motion is oscillatory in nature, and the amplitude will decrease or decay exponentially with time. So in case of underdamping vibration, the card will keep on bouncing with decreasing amplitude until it comes to steady state. তো গাড়িটা কি হবে, বাউন্স করতে থাকবে অ্যাজ দ্য মোশন ইজ অসিলেটরি, এবং এটা বাউন্স করতে থাকবে যতক্ষণ পর্যন্ত না এটা স্টেডি স্টেটে রিচ করে। Third one, when it follows a critical damped vibration, then what will happen to the car? In case of critically damped vibration, the motion is non-oscillatory in nature, but it will return back to the initial position of rest, and the displacement will follow a very fast decay. That means in critical damped vibration, the motion of the card will be non-oscillatory, and the card will return back to its position of equilibrium as fast as possible. That means এটা খুব ফাস্টলি এটা ওর ইকুইলিব্রিয়াম পজিশনে চলে আসবে। So this is the practical example for a bouncing car under overdamped, underdamped and critically damped condition. The second, we will discuss about another type of example. Categorize the type of vibration for the following cases. Number 1 is automobile shock absorber, number 2 is swing door, and number 3 is door closer. Now for automobile shock absorber, the displacement of the car, that means displacement of the vehicle or the automobile, will come to its rest position as fast as possible. So in case of automobile shock absorber, the type of vibration would be, or type of damped vibration would be critical damping. In case of swing door, the movement of the door is back and forth about its equilibrium position, and it will come to rest after a certain time, where the decay of the displacement will occur very slowly. So swing door is motion is oscillatory in nature, so it would be underdamped case. In case of door closer, the vibration would be overdamped, because in case of door closer it takes very longer time compared to other two vibrations to reach to its initial position of equilibrium. So for door closer it would be overdamped condition. So this is the end of today's lecture. You can also watch my other videos. The link are given at the end of this video. Subscribe the channel and press the bell icon. See you in the next video. Till then, bye.